Good evening, everyone. Welcome to Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCCPS IISc. It is my pleasure to introduce today's speaker, Professor Sayak Chowdhury. He will be speaking on Nash regret and beyond, optimal fairness guarantees in bandit problems. Professor Sayak is an assistant professor in the Department of Computer Science and Engineering at the Indian Institute of Technology, Kanpur. His research focuses on sequential decision making under uncertainty, including multi-armed bandits, reinforcement learning, and language model alignment, as well as on privacy and fairness in ML. Prior to joining IIT Kanpur, he was a postdoctoral researcher at Microsoft Research India and the Boston University. He received his PhD from IISc Bangalore. He is a recipient of the INAE Young Associate Award from the Indian National Academy of Engineering. Over to you, Professor.
So today's talk is about bandit problems. There is a line of work I am doing with two of undergrad students, Dhruv and Nishant. Both of them have now graduated, and so we started with standard bandit problems and then extended to linear bandit problems. Today we are going to focus on standard bandit problems. So here is a roadmap. First I will introduce what a bandit problem is and what are several regret measures. Then I will motivate that why standard regret measures in bandit problems hide fairness notions. They cannot capture fairness notions. And this will help us to introduce a new definition, Nash regret, or which is based on a philosophy in social choice theory called Nash social welfare. And then we will define Nash regret, and then we will give our algorithm and show that normal UCB algorithm that we know about in bandit problems works here also. So then we will extend this to some more general fairness notions, which is called the P-min family. Then finally, if I get time, I will talk about Nash regret in linear bandits, and I will conclude with some open problems. Okay, feel free to stop me at any time if you have some doubts. So first introduce bandit. So I hope everyone knows multi-armed bandit problems, right? So there are k arms, right? And each arm is associated with k parameters, mu1 to mu k, and all these mu1 to mu k parameters are unknown. Right? You can think about each arm is associated with a Bernoulli probability distribution with parameter mu1 to mu k, or Gaussian probability distribution with means mu1 to mu k with known variance. You can think about that. So bandit problems have found several applications. It has started from 1933 by Thomson in the drug trials. So there are T agents or T users, and K drugs will be administered among these T users. The users will come one by one, and a drug will be administered to the user, and its effect will be monitored. And based on this observation, when the next user arrives, we need to design which drugs to prescribe to that user given all the history of observation that we have acquired till now. So this is a standard sequential decision making problem with partial observation, because we can only know the effect of the drug after it is administered. So we can model this as bandit problems. So the goal in here will be to find the best possible drug. So out of these T agents, we keep on administering the drug. Our goal will be to find the best possible drug. Similarly, a modern day example is displaying ads. So there are T users which are logging into a website in like Amazon, and K ads can be, there are one ad out of these K ads has to be shown to the user, so that if the user clicks, and the revenue maximizes. So we have to show the ad which has the highest likelihood of the user clicking and say buying the product, right? So this is also a bandit problems. k ads or k arms, and we need to find the highest revenue generating arm among the T users. Okay, so how a bandit learning, bandit algorithm goes by, right? So their learning happens in round, and each round will pull an arm. Say at the first round we pull this arm 2, right, and we receive a reward y1, which is a random draw from the probability distribution associated with that arm, right. So if it's a Gaussian distribution, it's a random draw from a Gaussian distribution with mean mu2. So with this observation y1 now at our hand, we need to choose which arm to select next in the next round. Say in the next round we choose arm 1 and we observe a random reward from that arm. The learning goes round like that. In round 3 we choose say arm 3 and we get a random observation from that arm. Its learning goes like that. Similarly, in round 4 we can select some arm based on the observations, and we can write down the algorithm in some words. So the algorithm as follows. So algorithm, any bandit algorithm, it has sample access to k probability distributions for t rounds. That means algorithm can sample from probability distributions. So at each round small t, algorithm select an arm it and receives a random reward. Okay, so note that this arm it, right, this is a random variable because this will depend on all the past observations. Past observations mean past random arm pulls as well as random observed rewards. So this is a random variable, so algorithm selects this arm. So once this arm it is selected, algorithm observes the reward yt, right, and now if I can compute the expectation of the reward yt, it will be like this. It is the expected value of the mean associated with that particular arm, right, mu of it, right. For example, if it is say 2, right, it is the random arm 2, so the expected reward will be expected value of mu of 2. Okay, so why I call expected value of mu of 2? Because it is itself a random variable, right. So it's an expected reward. So this expected reward has nothing random in it, right. Whatever randomness was there, we have already taken it out. So this is the expected reward an algorithm will receive at round t. And the benchmark is the arm with the highest mean. So there are k number of arms, each having mean mu1 to mu k. The benchmark is the arm which has the highest mean, that is the optimal arm. The algorithm is after that arm. So obviously, since we do not know mu1 to mu k in advance, we will suffer some cost or regret. That has been captured by this formula. This is the regret or shortfall in rewards of not knowing the benchmark mu star in advance, right. So if we know the benchmark mu star in advance, that means if you know mu1 to mu k in advance, we could have already commit to the best arm. Since we do not know that in advance, we keep on playing different arms it, right, and for that every round we suffer this regret or shortfall, which is mu star minus expected value of mu of it. So if I take an average over t rounds, so and I call it average regret over t rounds, or I call it average expected regret over t rounds. So note that we take the difference of average expected rewards, right. There are other notions of regret also, where instead of expected value of mu yt, we just work with the random rewards, right, yt. So mu-i's are the true means. Yeah, so I have already averaged out the realizations, right. Okay, so there are realization yt. Yt is drawn from a probability distribution with parameter mu yt, with mean mu yt, right. If I take an expected value over yt, I will get mu of it, right. If I take the reward randomness out, then I take another expectation to take the armed or randomness also out, right. So this is the expectation over both the reward draws as well as the arm draws. Okay, so there is nothing random in this quantity, right. So it's a completely deterministic quantity, and we want to bound it. bounded and we want to make sure over capital T rounds this quantity goes down to 0. If we keep on increasing capital T, this quantity will be negligible. That's our goal. Okay, so now this is a brief intro to multi on bandits. Now let's come to fairness. So this average regret that I have defined, I will show here that this is not a fair metric in the following sense. Consider the drug trial example. A sequence of patients are coming in, right? And when each patient arrives, we administer a drug and measure its outcome. So consider this scenario for early patients, right? We do not have any information a priori about which is the best drug. So intuitively, we will probably not be able to administer the best drug or the good enough drug to the early patients. So the ex ante value or the ex ante value, or you can think about the kind of average value, right? Or you can think about the average quality of treatment received by the early patients will be very low. So I have denoted it as 0. Here I am assuming that all the means are greater than or equal to 0. So let's not think about negative means, right? It can happen and we can model it, but just do the shift and assume that all the means are greater than or equal to 0. So low value is very close to 0 and the high value is somewhere like mu star. Okay, so early patients, right, the average, on an average the treatment they will receive will be very low because we do not have any information. So that's why I am denoting as ex ante value. That means that on an average reward which the early patients got, right? These are not realized reward, these are only on an average that rewards. So intuitively early patients will have very low reward, and the late patients, once we have acquired sufficient information, we can think that late patients will get high reward, right? The average reward or average treatment received will be high, right? You can think about it will be very close to the optimal reward. So some patients will get, early patients will get 0 reward, 0 average reward, and late patients will get high average reward. However, the average value, total average value can still be high if we can ensure that the number of early patients doesn't grow linearly with number of rounds. It only grows sublinearly with number of rounds. Think about number of early patients is log of t. If capital T are your total number of patients, and think about number of early patients are only logarithmic in t. Even if ex ante reward for logarithmic number of patients is 0, average value can still be very high because the late patients are getting good reward. Okay, so this is a very good, it's a good metric in utilitarian sense because the average reward is high. However, not fair for the early patients, right? The early patients will still get an average 0 reward, right? So this notion of average reward or average regret doesn't capture fairness. So it's not a good not a metric for fairness. So now think 2 examples. There are 2 algorithms, algorithm A and algorithm B. So this is the number of rounds, there are t number of rounds. Each round a patient or an agent arrives, and the algorithm does its recommendation and the patient gets some value. And by value you can think about the expected reward or the average treatment. 2 algorithms, one algorithm completely ignores early agents, just give them 0 average reward, right? Half of the agents it gives 0 rewards, rest half it gives half reward. Okay, average is 1/4, right? If I take the average about capital T patients, it's 1/4. Another algorithm B, which spread the exploration out, it equally gives 1/4 reward to all the patients. Average is still 1/4, right? So on an average, both the algorithms will perform similarly. However, algorithm A is completely, ignoring early patients. It's not fair to the early patients. Whereas algorithm B, by just spreading the exploration out uniformly, it is favoring all the patients equally. So this algorithm is more fair than the previous algorithm, while both maintaining the same average utility, which is 1/4. Okay, so identical average reward. So this example tells that average regret cannot tell which is a fair algorithm. If you just only look at average reward or average regret, it cannot tell which is a fair algorithm. Both algorithm is performing similarly. So we need a performance measure that can tell this apart, right? Which algorithm is fair or which algorithm is not fair. We need a performance measure like that. So we need a metric that actually takes the collective social welfare in account. Do not ignore any particular users. Okay, we need to define a metric like that. Okay, so any questions? So now let's define this metric. So call it fairness by design because we are defining a metric which will give us fairness, right? And then we'll design algorithms which will satisfy fairness, satisfy this metric. So let's define the metric. There are t number of agents and each agent will get some value, positive value, v1 to v capital T. Okay, so given these values, our goal is to come up with a welfare function which takes this sequence of values as input and gives a non-negative number as output. So there are several possibilities of designing a function, right? You can think about this function is nothing but a aggregator. Take a sequence and aggregate them in some way. One aggregator we have already seen, which is your average aggregate. Take the values and take the average of those. So this is your average reward, and this is in welfare terminology it is called social welfare. Nothing but arithmetic mean of the sequence. Another extreme is something called the egalitarian welfare, which takes the sequence and give and assign the welfare value of the sequence is the minimum value in the sequence. This is called egalitarian welfare. So this egalitarian welfare is telling that we need to ensure the poorest person in the society also have a good amount of wealth, right? This is called egalitarian welfare. Obviously this is too hard a metric to ensure, right? You need to ensure the poorest person in the society also have a good amount of wealth, right? So there is some metric which sits in between, which is called Nash social welfare and designed by none other than John Nash, which tells that instead of taking average or arithmetic mean of the values, we will take the geometric mean of the values. Okay, this metric is called Nash social welfare, and this sits perfectly in between because of this relation. We can show the geometric mean is always less than the arithmetic mean by the standard AMGM inequality. Similarly, geometric mean obviously has to be higher than the minimum value of the sequence by definition. So this sits perfectly in between in these two extremes. On one extreme is the arithmetic mean, which doesn't care about fairness, and another extreme is the egalitarian welfare, which cares only about fairness. That means it ensures the minimum, the person who has minimum wealth in a society still have a good amount of wealth. It only cares about fairness, it doesn't care about any utility. Nash social welfare happens to balance these two out. For example, like consider our earlier example, there are half of the agents on one algorithm gives half of the agents 0 reward and another half reward. Another algorithm gets 1/4 reward to every arm. You can see the social welfare, which is average regret, is same for average reward is same for both. But now if I compute Nash social welfare, so what will be the Nash social welfare for this algorithm? Can anyone tell? 0, right? Because there is 0 present here. If you take the product, it will be 0. And what will be the social welfare? Nash social welfare for this one. This will be 1/4, right? All are same. So as you can see, the Nash social welfare will be less than in the first algorithm, which doesn't care about fairness, but the Nash social welfare will be higher for the second algorithm, right? So this is a good metric to maximize. Okay. Not only that, the Nash social welfare satisfies some nice properties. There are axioms in social choice theory. Nash social welfare is the unique welfare function out of the all possible welfare function that one can design is a unique welfare function that satisfies these 4 properties. Scale invariance, that means if you take the utilities or the values v1 to vt, right, and suppose instead of reporting the values by rupees, instead of rupees someone report the values in dollars, right. That means people report a scale change values, right. That doesn't change the ordering of 2 allocations. Take 2 allocations, right, 2 set of sequences v1 to vt and another set of sequences v1 prime to vt prime. Even if some of the agents report their values in a different scale, the ordering doesn't change. This is scale invariance. Similarly, Pareto efficiency, that means if out of these t agents, one of the agents receives bigger wealth than the currently reported one, the overall welfare still increases, right. This is called monotonicity or Pareto efficiency property. Symmetry, if we swap 2 agents, doesn't change the welfare. And independence of irrelevant attributes, that means if you compare 2 agents, right, who is wealthier than the other, that doesn't depend on a third person in the society. Right. This 4 property this welfare metric satisfies. It turns out it is the unique welfare metric that satisfies these 4 properties. There is another important property satisfied, which is Pigou-Dalton inequality aversion, which tells if I take, it follows the Robin Hood criteria. So if I take some money from a wealthy person and go give it to a poor person, right, which this action increases the geometric mean of the population. If I take epsilon amount of money from a wealthy person, of a person with high value, and give it to a value with add it to a person with low value, it increases the Nash social welfare. So these nice properties is satisfied, and the second property is basically telling about fairness in the society. So with this being established, we are now going to work with Nash social welfare as our metric for bandit problems. Okay, any question till now?
I suppose the algorithms that we design by minimizing the social welfare will not hold true for minimizing Nash social welfare.
Yes, if we design an algorithm which minimizes social welfare, it will not hold true because social welfare is always higher than this, right? And in the next slide I will tell you why it won't hold true. Next slide, allow me some. Okay, now what are the values, right? I am talking about each agent will receive some values, right? So what are the values in bandit problems? So what happens in bandit problem? At each round an agent is handed a lottery, right? What is this lottery? So algorithms history dependent choice of arm, that means an agent and user comes and arm has been pulled, right? So this arm pull IT, capital IT, is history dependent choice of arm, and after the arm is pulled, algorithm receives a noisy reward YT, right, Y sub t. So this 2 randomness is present. So the value we define, the agent's value at every round is the value of that lottery before the lottery resolves, before you get to see the actual outcome of that lottery draw, right? That will tell the value of that agent. By definition, Vt is the value of that agent at round t is expected value of mu Yt. Okay, so there is no randomness present here, right? So before the lottery has been resolved, that is the value we assign. Okay, so this is the value of each agent at round t. Vt is expected reward. Okay, so no randomness there. So now one might ask this question, why not using the realized reward, right? The actual reward that I receive from the random draw from the distribution, why not use that as a value? Why use the value before the lottery results? So now this is I feel this is a question of debate. I still don't have a clear clear answer that why not a realized reward. I can only give some justifications. So first justification that I present here, that the algorithm cannot control the noise in the random draws. So if we just scoring the realization, random realizations, it has some amount of luck in it, right? If I draw from a Bernoulli distribution, whether it will come a heads or come a tails, it's had some amount of luck in it. We cannot just score realizations in the fairness axis, right? So if we want to score two algorithms in the fairness axis, it's better to score two algorithms using their expected rewards, not realized rewards. Second justification that I want to give is that realized rewards can be unbounded below. Think about Gaussian distributions. Realized rewards can be negative, right? So now a product of the realized reward doesn't define welfare. If I have all the negative values, right, or two negative values, the product still becomes a positive value. How can we justify the product high, right? Even if product can be high, even if two high negative values, the product can still be high. So as it turns out, the geometric mean is not defined for negative numbers also. So by definition, realized rewards doesn't make sense. And the third one is related, that a randomized rule, a randomized algorithm is fair only ex ante. If we take ex post, that means after the realization, somebody will always lose the coin flip due to the randomness. So these are my justifications, and also justification given in prior work to work not with realized reward, instead work with ex ante values. Okay. So now, why didn't this issue, right? Why working with ex ante values so important in the fairness axis, not in the utility axis, right? In utility axis, we have algorithms which work with realized rewards. Why it didn't came up for those algorithms? Because if you only care about the arithmetic mean, the distinction between ex ante and ex post is invisible. If I take the expectation of the average realized rewards, right, it is same as expectation as of taken the average of the expected rewards. The expectation, by linearity of the expectation, it just goes in. So for utility metric, this doesn't pose an issue. But for our metric, which is a Nash social welfare, which is a product, geometric mean, we need to make a choice. Whether we take the geometric mean of the realized rewards, or we take the geometric mean realized rewards and then take the expectation, or we take the geometric mean of the expected rewards. We need to make the choice, since both are not equal. The expectation doesn't just go in. So we make this choice in this work that will take the geometric mean of the ex ante rewards or the expected rewards. Okay. So this is a question of debate. We will come back to it later.
The first one I don't agree with. The YT submission might depend on how many times you sample which arm, right? And then even though the name of whatever that IT does, right? It depends on the. So suppose you got ITs to be the best arm first, right? Then the right hand side will be just mu star, whatever.
Yeah, if you just always IT is the mu star, right? Say always you get IT equal to the best one, right? Right hand side is mu star. Left hand side will also be mu star.
So what I mean is that this IT has certain choice, right? The first one is not clear that is what is.
Yes, yeah, in the definition I didn't put the randomness over IT here. Here it's to be randomness over IT also, and randomness over the realized draws. So you can do conditioning, right? Conditioning on IT.
So the way you should have done the expectation should have been condition on.
Right. Condition on it, then take another expectation. Right? I should ideally, I have suppressed the tower property here. So what changes? Only the aggregator changes. Instead of the arithmetic mean, I will work with the geometric mean over the ex ante values. Okay. So this will be our metric. So now let's define regret in this setting. So recall this was our Nash social welfare, and the regret, if we consider the social welfare, it was just average regret, and instead if we consider Nash social welfare, it is just same benchmark minus the geometric mean of the ex ante rewards. And using AM and GM inequality, we can see that Nash regret is always higher than the average regret. So this answers your question that if I have an algorithm which upper bounds Nash regret, suppose I can develop an algorithm which upper bounds Nash regret, it can also upper bound average regret, but not the other way around. I cannot have an algorithm which cannot directly apply an algorithm which upper bounds average regret and claim that it upper bounds Nash regret also. So it's a harder metric to minimize. So even if we can ensure the Nash regret is minimized, it automatically tells the average regret is minimized. Okay, so what we get, right? So we want a low Nash regret, and what does that give to us, right? What it gives and what it doesn't give, right? So I think I should go there maybe. Okay, so let's fix this. Fix the horizon T upfront. The goal is to minimize Nash regret. So my definition of Nash regret is benchmark minus the Nash social welfare over T rounds, which is the geometric mean of ex ante rewards. So now we can use this result, which is average over log shortfall, log of mu star, which is the benchmark, divided by average reward received at round T. Right? This I calling as log shortfall mu star divided by expected value of mu yt. So you can see, right, this quantity log of mu star divided by expected value of mu yt is a positive, non-negative, because mu star is always greater than mu yt, right? Mu star is the highest number greater than or equal to. So this is a positive number, right? So we want this value to small, and we can use the definition of Nash regret to write this value as log of mu star divided by mu star minus Nash regret. It's just algebraic manipulation. I just substituted, I just took the summation inside of the log and that became product, and I got the geometric mean. I just substituted this. So now what it gives, right? If I just take mu star and divide the upper and lower, the numerator and denominator by mu star, I get log of log of 1 minus 1 upon R Nash minus mu star divided by mu star. So now, so if R Nash divided by mu star is much less than 1, I can just use this coarse approximation, that is R Nash of T minus divided by mu star. So what does this give, right? If we can make the Nash regret vanishing with T, this will make sure the average log shortfall, this quantity, also vanish with T, right? This will make sure. And there's a nice consequence we can get, right? Just using Markov inequality. Consider this experiment. So we have capital T in number of rounds up front, fix this T horizon up front, and randomly sample one round, small t. Okay. Then using Markov inequality, where the probability or the randomness over this uniform random draw from the round draw of rounds, and using Markov inequality you can show that the fraction of agents, right, fraction of agents, the left hand side, fraction of agents which has less expected reward, a low expected reward, that is the expected reward is less than mu star by some constant c, right? C is a constant which is greater than 1, think about C is 10. The fraction of agents which has the expected reward less than mu star by 10, that number actually small if Nash regret is also small. That number is actually less than or equal to Nash regret divided by mu star. Just this is the application of Markov's inequality. What does this give, right? If we can minimize Nash regret or make sure the Nash regret is small, the fraction of agents which receives very low reward, low expected reward, that will also be small. And that's what we all want, right? We do not want any agent to starve, right? We want each agent to get at least a good amount of expected reward or ex ante reward. So minimizing Nash regret will ensure that. So what it promises? It promises that nobody is written off. Each agent should get some expected or ex ante reward. if expected value of mu is for th agent is 0, then you know, right, Nash social welfare will collapse by definition, right. If one of this term is 0, this geometric mean will go to 0, it will collapse, and the Nash regret will be a constant regret which you do not want, right. And minimizing Nash regret will ensure that this doesn't happen. If we can minimize Nash regret. By minimizing, I mean the Nash regret should go down with number of rounds t. But it doesn't promise that every agent will get the best term. It doesn't promise that from the start itself everyone is getting the best term or close to the best term. It doesn't promise that, and it is impossible because we do not know mu1 to mu k in advance. So we have to explore, right? Exploration is not discontinued here also. We need exploration, and then if we can gather sufficient information, then we can exploit. Okay. And how to explore then? So we know that we have to explore. Then what is the easy way to explore, right? Each agent comes, we need to do some exploration. Easy way to explore is do some uniform exploration. Uniformly pick an arm and assign to the agent. We are going to do that, and we will see that uniform exploration is not unfair. It retains fairness. How? If I at round t I uniformly select one arm from the k arms, then probability that it is equal to I is 1 by k. And then we can show that expected value of mu yt, which is the ex ante reward, is nothing but 1 by k summation of I equal to 1 to k mu y, just the average, because probability of it equal to I equal to 1 by k, right? So expected reward is the average reward, so it is always higher than mu star by k. So uniform exploration automatically gives us this thing, right? Whichever round we do some uniform exploration, we will ensure that ex ante reward is always greater than mu star by k. And if k is 10, it's always greater than mu star by 10. So uniform exploration by definition giving us fairness, right? So for first initial rounds we can safely do some uniform exploration. It will give us fairness. Obviously, it will not give us any information about which arm is the best. We want that. We want to ultimately select arms which are the best ones. So for that we need to do some exploitation also. And to do that, we are going to fall back on the classical UCB algorithm of multi-arm bandits. So let's recap what is UCB algorithm. So every round t, say each arm is sampled ni times, and we observed their rewards and computed their empirical means mu hat of I. And then define an index called UCB, which is empirical mean plus a variance corrected term, which is square root of some log t divided by ni, which is the number of times the arm has been pulled. This rule tells if some arm has high empirical average, it will have high UCB index. If some arm has been pulled less number of times, it will also have a high UCB index, because we do not have any information about that arm, so we better pull that arm to get some information. And the algorithm works as follows. For each arm, each round we have these mu hats computed, and we have these confidence bounds, confidence intervals computed. So the upper point of this interval is your UCB index. For each interval, the upper point is your UCB index, and the width is this square root 2 log t by ni. So with this, we select the arm which has the highest UCB index. Okay, and the choice of this width is coming from Hovding inequality. It tells that the empirical mean is epsilon distance away from the true mean, with probability which is going exponentially down with number of samples. The choice of width is coming from this Hovding inequality, and if we play the arm which has the highest UCB, we will always ensure the regret is order of square root k by t. That means going down, with t. Okay, so this is a classical algorithm. We are going to use the same algorithm here. So before that, let's talk about a prior work by Professor Siddharth Burman and his group in CSE department. So they came up with this notion of Nash regret in their paper 2023, and they argued that UCB algorithm is not suitable for minimizing Nash regret. Instead, they propose a new index which is called Nash confidence bound index, which is a bit different than the UCB index. Same empirical mean is there, but the variance corrected term is also a function of the empirical mean. That's what their proposal is, and they show that we perform uniform sampling for square root t number of rounds and then select the arm with highest Nash confidence bound index. And this simple tweak to the UCB algorithm gives order of square root k by t Nash regret. That's what they showed. And they did the analysis because the confidence width changes, so standard Hovding bound will not apply. They did the analysis using multiplicative Chernoff bound, okay, to get the tighter confidence sets. Now, if you are aware about this multiplicative Chernoff bounds, you know that these bounds will hold only for non-negative and bounded rewards only. Only if the realized rewards are non-negative and bounded. This is a special case. Think about rewards bounded in 0 to 1. These bounds will hold only for that. So it actually limits the scope of the algorithm. But in practice, rewards might not be bounded. Like rewards can be coming from a Gaussian distribution. For that, this entire algorithm doesn't work. So we ask this question: what happens when the rewards are not bounded? Right? Rewards are Gaussian or sub-Gaussian or others like sub-exponential. In this work, we focus on sub-Gaussian rewards, but can be extended to distributions beyond that. So we ask these questions and we show and we propose that okay, we can go back to UCB. It's not that we need to define a new confidence index, but we can just only work with standard UCB algorithm with a small tweak. Instead of performing uniform sampling for a deterministic number of rounds, square root t number of rounds, which is deterministic in advance, we tell that we do it for some random number of rounds. And in the second phase, instead of selecting arm, which is maximizing the NCB index, we propose select the arm maximizing the UCB index only. With this simple two tweaks, and the third one, and this UCB index just for the sub-Gaussian rewards with unit variance, UCB index is like that. If a variance is this. And the third one, which is most important, we design a stopping rule when the uniform sampling will stop. So we will stop phase 1, the uniform sampling, at the first time t, when for some arm I, the number of terms the arm I has been pulled exceeds this value. This is our stopping condition. We keep on doing uniform sampling until this condition is satisfied. Whenever for some arm I, the number of pulls of that arm I is greater than log t upon the square of its LCB index, which is lower confidence bounds index, right? We'll keep on computing every time, and whenever for some arm I this one satisfy, we'll stop. Phase 1 has been stopped, and then we will commit to phase 2. Phase 2 is whatever UCB index we compute for all the arms, just keep on running the UCB as it is. This stopping rule ensures that the stopping time, right? The stopping time is order of k log t divided by mu star square, right? So this stopping rule ensures, and this tells that the stopping rule is neither too high nor too low. It's neither too low that we don't get any information, right? Nor too high so that we just keep on uniformly exploring, right? It sits perfectly in a balance which gives us sufficient information. And then phase 2 will start once confidence is strong enough, because we have got sufficient information about all the arms. We can compute their UCB index. UCB index are well concentrated, and then we can keep on running UCB, which will deliver square root k by t regret. This is for sub-Gaussian, yes. So if there is a point, right? So if means are negative, right? The point is we cannot define the geometric mean. So note that the geometric mean is the product of the means, right? So if means are negative, the geometric mean definition doesn't make sense. So you have to assume that means are greater than or equal to 0. but the random draws can be anything. Okay, random rewards, random draws from the sub-Gaussian distribution which has positive mean or non-negative mean can be anything. So this is what our contribution is. We get order of square root k by t Nash regret for sub-Gaussian reward also. Okay, so this is a basically scope improvement work over the prior one. But there are some more consequences of our new algorithm. So we can now encompass a variety of fairness definitions. Instead of only focusing on the Nash fairness definition, right? Nash social welfare, we can now encompass a variety of fairness definitions, which the prior work cannot. So let's now go beyond Nash social welfare. Generalize this notion to the p-mean welfare. So the same setting, there are sequence of values v1 to vt. We can define a generalized p-mean welfare with p takes values from -infinity to +infinity. It's defined as that. It is the power mean of the sequence. Okay. So now why I call it generalized welfare? If I take limit p tends to 0 in this equation, it will get the Nash social welfare, which is the geometric mean. If I take p equal to 1, I will get the arithmetic mean. If I take limit p equal to -infinity, I will get the egalitarian welfare, which is minimize over t. So as you can see, by varying p from this interval -infinity to 1, right? Interval beyond 1 doesn't make sense because at p equal to 1 we hit the social welfare limit, right? Everything beyond that is more utilitarian, no care about fairness. So -infinity to 1 is our region of interest. By varying p from -infinity to 1, I can encode different degrees of fairness. P equal to 1, social welfare, no fairness at all. If we keep on reducing p, we put more and more emphasis on the fairness, with the fairness becomes the highest important factor when p equal to -infinity, and keep on losing a bit more on the utility side. Okay, so p is a knob, right, which is tuning this fairness and utility. You can tune this knob accordingly. What kind of thing we want? If we want more fairness, put p to the negative side. If we want more utility, put p to the positive side. And Nash social welfare sits perfectly in the middle. So with this, we now try to characterize the p-mean regret of our algorithm, which is nothing but the benchmark minus the p-mean welfare. And we show that the same algorithm, same structure, with a little bit of modification on the stopping rule, depending on the fairness level that we want, depending on the p value, p we want. Our stopping rule will stop when for some arm I, number of pulls is greater than some Cp. C is a constant depending on the fairness level p, times the same value that we considered when minimizing Nash regret. Only one later modification to the entire algorithm, and we can give the entire family of regret bounds. And the value Cp that we set is, if p is greater than or equal to -1, then Cp is 1. That means it's the same algorithm. P greater than or equal to -1, both the minimization of Nash regret and minimization of p-mean regret, the same algorithm. P less than -1, which is the tougher regime, right? More and more focus on fairness. So there we need to put Cp equal to p square. So as you can see, we need to explore a bit more, right? We need to wait till some arm has been pulled a lot more number of times, because Cp is now p square. Think about p equal to -2, so p square is 4. We need to wait 4 more times. Then we are waiting for the other values of p, right? Because regret metric is getting tougher and tougher. We need more fairness, so obviously we need to pay some price on the utility. For that we need to wait the phase on to stop, and obviously that will price in the regret. So the regret bound, p-mean regret bound is same, right? The same Nash regret bound times a function of Pn, number of arms k. Where obviously if p is greater than or equal to 0, the values are same. And if p is less than 0, our bound is growing polynomially with k. K is k to the power mod of p by 2. And obviously if p greater than less than -1 is the pain point. Think about p is -3, then it will be k to the 3 by 2. So that's the pain is coming, right? So it tells that there is no free lunch, right? If we want more and more fairness, strict fairness, obviously you need to pay in regret. There's no free lunch. You cannot expect very high amount of fairness and you do not suffer any utility. P equal to -infinity, your regret will become infinity, right? This you cannot do anything. Okay, so in this paper we did this, but then we figured out that this is not the correct scaling, right? We prove an upper bound. Then in a follow-up work we figured out, because we was not able to prove the lower bound in that work, then we started proving the lower bound and figured out that okay, this is not the correct scaling of the p-mean regret. The correct scaling we found is this. But if p greater than -1 greater than or equal to, then it is 1. If p less than -1, it is k to the power mod p -1 by 2. So we are able to get the scaling down a bit. And by proving matching lower bounds, we are also able to show that this is the correct minimax optimal scaling. This is another paper which is new and which is under review. So currently this is the stage, right? This is what we get, the minimax optimal scaling for p-mean regret in KM bandits. That's what we get. So I have some time, 5 more minutes, okay. But if you have any question about the proofs, catch me in offline, okay, I'll discuss. So here are some numerics that tell that whatever we are claiming in theory works out in practice. So here is this sub-Gaussian rewards, and here is if you run the standard Nash confidence bound algorithm from Berman et al.'s paper versus you run our algorithm, which is blue line, you can see for sub-Gaussian rewards we are performing much better than them. Nash regret starts plateauing decreasing much earlier, and obviously different values of p also. We know, right? If p is high in the negative side, metric is tough, right? You can see, right? This curve, this blue curve is p equal to -5. You know, Nash regret, the p-mean regret starts going down a lot later in t in number of rounds. Wherever if p equal to 1, which is only the utility metric, right? It starts going down much earlier. So you can see, right, the entire range of variances, right? So everything proposed in theory or claimed in theory also validates in practice. So in this now the last 5 minutes I will talk about that Nash regret in linear bandits. So whatever we talked about ports directly to the linear bandit setting, also with some proper modifications. So linear bandits is a functional form of bandits. Here each arm is a vector in d-dimensional Euclidean space, and playing an arm IT gives you a reward which is a linear function of the arm's features and some Gaussian noise, right? And the weight parameter theta is unknown and we need to learn it. But each arm shares this parameter. So there is a structure among the arms. And the well-known algorithm is a lean UCB algorithm which tells, right, you collect rewards, play actions, collect rewards, right, and build a point estimate theta hat t, which is nothing but your ridge regression solution. You collect data like this. Data is linear with some noise in it. So you can use a least square solve a least square problem and get your point estimate. Similarly, once you get a point estimate similar to UCB, you can build a confidence interval around the point estimate. In this case, it turns out to be ellipsoid. And you play the most optimistic action with respect to this ellipsoid. Right? Your action IT is the arm which maximizes the maximum possible reward from this ellipsoid. This is an algorithm. And it has been shown that it achieves order of d by square root t regret, which is optimal. So Siddharth Burman and his group also published a paper using their Nash confidence bound idea that instead of UCB, if you use Nash confidence bound, you will get d to the power 5 by 4 square root t regret, but their bound is only for positive rewards. When the open problem they posed in their paper, we know the correct lower bound is d by square root t. So there is a gap of d to the 1 by 4. That problem was posed as an open problem. And obviously general sub-Gaussian rewards are also known in the prior work. And you can guess that in our contribution will be to back to UCB and solve the open problem. And exactly we did this using the same kind of stopping time rule, obviously modified according to the linear bandit structure. I will not go to details, but you can get the same idea. First couple of rounds will be some kind of uniform exploration, and then you will commit to a lean UCB algorithm. So with this I will stop on future directions. So we took it from say bandits to linear bandits, right? It's a linear structure. So now if there are non-linear structure in rewards, for example generalized reward models or kernels, right? Rewards are coming from a reproducing kind of Hilbert space or something like that. Then can we build an algorithm which minimizes Nash regret? This is an extension which is not straightforward. We have tried it, but not to much got hold of anything. But I present an hypothesis of some of you can take it and pursue further. My hypothesis is if you have some bandit problem, some nonlinear structure, your first point of attack will be take an any optimistic or UCB style algorithm which is known for that particular problem, for average regret minimization problem, right? So take GLM bandits, average regret minimization is a solved problem there, right? And there will be an UCB style algorithm available. Take that algorithm and then devise a two-step strategy. First, a uniform arm exploration strategy for phase 1. So what is the definition of uniform here? It will vary. And then a new stopping rule using the regret bound available in the literature, the average regret bound which is available in the literature. Use that bound to design the stopping rule and those UCB LCB index. So this my hypothesis is that if we can solve this two-step for any bandit problems, we can get a hold on their Nash regret. And the second point, which is more philosophical, which is the notion of fairness with ex post rewards. In this entire talk, we were focused on the notion of fairness with ex ante reward. That means the average rewards, right? Expected value of mu yt. But what is the correct notion of fairness when we only work with realized rewards, right? Which is random rewards y1 to yt. What is the correct notion of fairness, right? Is there a different notion similar of fairness exist who will satisfy this social choice axioms also? So this is a nice open directions, and if we can get some handle on it, right? If you remember in our algorithm, we always tell that okay, we need to know the number of rounds capital T in advance, right? But a true sequential learning algorithm will never know what is the capital T, how many users are going to come. We never know that, right? So if we have a different notion of fairness, then how can we build an algorithm which works for any value of capital T, which is not known in advance? For that we need some machinery called anytime valid confidence sets, which are there for average regret minimization problems. But what will be that in this framework? This is the most interesting open question. With this I stop and I'm open to take questions.
Okay, if there are no questions, let's thank the speaker for accepting our request and delivering an interesting talk. Thank you. Thank you everyone for attending. We have arranged refreshments in the coffee hut. Please continue your discussions there. Thank you.
Thank you. Thank you for inviting.